All right, these are the calculations for our loop-de-loop or marble track. So we were required to fit a marble track through a 2-foot loop, which 2 feet is about 0.7 meters. We just rounded up to 0.7 meters. So I took it in sections, decided that this will be V2, the height, the velocity at the top of the loop. And then since we have kind of a transition here between a straight portion and the start of our loop, I wanted to take this into account in our first energy conservation equation. So finding V2, all we had to do was take a normal acceleration in a radius. So we used the normal force plus the mass of gravity equals mv squared over rho. And just to be safe, I wanted to calculate as though our marble would have the same force of gravity going up against the track, or our normal force would be equal to gravity. So I just set our normal force equal to gravity, so we have 2g right here. Mass cancels out of this equation, so you're left with 2g equals v squared over rho, which, solving for v, you get 3.132 meters per second at v2. Then you take that equation, or that answer from that equation, plug this into an energy conservation, and you plug it in as v2, and we solve for v1. And v1, right here, at the start of this, you get 3.8 meters per second. This is your rolling resistance. This 1.45 degrees was the angle at which we found that the ball begins to roll. So we take that angle, multiply it by the sine, and then you take your force of gravity in the x direction, and you get 4.6 times 10 to the negative third, which is not what we plug into this equation, because in this equation, mass cancels. So I had to take mass out of that, and this is what we plugged into the equation, 0.248 meters per second. I know it's strange to see rolling resistance as a velocity. So after we use our first energy conservation equation, we then again plug it into another energy conservation equation to solve for this height after this 0.5 meter portion of the track. Our V1 will be 0 because it will start at rest, and our V2 will be equal to 3.8 meters per second. This is gravity. Solve for change in y, and you get 0.74 meters at the very top of this track. Now we'll let Nick describe this ramp portion.
So moving on to the length of the jump calculation portion of the video. Started off, I got a height difference between the top of the loop and the jump right here, which I figured was 0.4437 meters. And with our conservation of energy, we have our potential energy here, which is mgh, and h is this height difference right here. And then our kinetic energy to solve for the jump velocity right here. So solving for jump velocity, I found that it was the square root of 2 times g times this height difference, which all that, it leads to about 2.95 meters. And that's the magnitude of the velocity here, which has y and x components. And so using constant acceleration equations for final velocity, it's 0 at the peak. So what I'm solving for is, you can see in this graph right here, the amount of time from the launch to the peak, which is t1, and your velocity y speaking is going to be 0 here because it's going to be starting its descent. So solving for t1 and for t2 so that I can get the total time so that I can solve for the length distance. So using a constant acceleration equation for t1, your final velocity is going to be 0 because you're at the peak. So that's the y component of your jump velocity minus the acceleration due to gravity times the amount of time, t1. And then so I solved for t1 and found, you can look at these equations here, they're beautiful, they're lovely, but t1 equals 0.21264 seconds. So this is the amount of time from the jump to the peak of the jump. And then using another constant acceleration equation for final velocity, which again is going to be 0, equals, I'm solving for the height length here. So again, your peak velocity is going to be 0. So again, it's your y component of the magnitude of the velocity squared minus 2 times acceleration of gravity times this h prime. Your h prime is the height of the jump there. So solving for that height, I found that the height, if you follow it down here, it's going to be 0.22178 meters. And that, again, that's the length of the height from the top of the parabola. And then plugging that into a third constant acceleration equation to find T2, since you have no initial distance, so this distance is 0 relative to this distance, so you have no initial distance, no initial velocity. So if you've noticed, I went ahead and canceled those out in one of the constant acceleration equations. And then so solving for T2, T2 equals the square root of h prime over 2g. T2 equals 0.2126366 seconds, or however long. So the total amount of time that the ball or the marble is going to be in the air is just T1 plus T2, which equals 0.4253 seconds. And then, so now at the time it's in the air solved, we have length of the jump. So we have the x component of the velocity times the amount of time it's in the air, so that's cosine of 45 degrees, times your magnitude of your jump velocity here, times the t total, and then the seconds go away, and then we get the horizontal distance travel is 0.8871 meters, or 34.925 inches. And in the video, we were off by 4.925 inches, so it traveled 30 inches instead of 34, and I only converted to inches so that it would be easier to use a tape measure. So we were off by 4.925 inches, or 0.1251 meters.
All right, this is our marble track. This is Nick Lease. This is the Thomas Lease. Mark Crane was over there, and I'm Jacob Jackson. All right, here we go. Wonderful. Let's just look at this distance right here.
I think it's right at 30 inches.
I don't know if you can tell from that. I'll zoom in over here. Fantastic. Our calculated distance for this jump was 36 inches.
34.
34 inches.
Right, yeah, 34.9, so 35.
This is
A couple inches off.
this is pretty good. Yeah.